In this workshop, Accellera working group, who's primarily focused on automotive safety, which is called FuSa. They will be sharing updates, what's happened over the couple of years, right? So for this session, we have 3 speakers. The first speaker is from AMD, Razin Gubin. Is a functional safety manager. He has over 18 years of experience in functional safety for EE systems and semiconductor by leading functional safety department in the Tier 1 company, right? Working in various semiconductor companies and holding various patents in the functional safety area. He is part of the ISO working group 8 through French delegation. He has provided various content on the ISO 26262 and Part 11 holds several patents in this functional safety area. And the second speaker is Jacob Wellington. He is the functional safety solution manager from Mentor, a Siemens business, and he's responsible for strategy and alignment of functional safety and high reliability technology across the portfolio of IC verification solution. He holds Bachelor of Science degree in Electrical and Computer Engineering from the University of Colorado. Prior to Mentor, Jacob held various design and verification and leadership roles, performing IC and SOC development at Xilinx, Micron, and Broadcom. The third speaker we have is Viren Wahab. Is the automotive functional safety verification methodology and lead at Qualcomm. He is responsible for coming up with methodologies for various FuSa verification activities and developing it across all automotive SOCs. He has over 18 years of experience in working in the semiconductor industry. Prior to joining to functional safety team, he held various leadership roles in design and verification domain. With that, we'll have the video playing.
Good morning and welcome to DVCon India and to this workshop that focuses on the Accellera Functional Safety Working Group. I'm Alessandra Nardi and I'm chair of the group, and with me today are Vareen Vahia from Qualcomm, Jake Wilton from Siemens, and Regis Gubian from AMD. So I will introduce them properly in a minute, but first let me tell you that today we would like to give you an update on the work and the progress the working group is doing to improve automation, interoperability, and traceability in functional safety. Let's skip directly to the agenda of the workshop. So I'll start with a couple of minutes introduction to the functional safety working group, some history and statistics, and then Vareen will take over the next section, which is describing the challenges, the mission, the scope, and the objectives of the group, and also how it fits in the standardization landscape. So Vareen is the automotive functional safety verification methodology lead at Qualcomm, and he's responsible for coming up with methodologies for various functional safety verification activities and deploying it across all of automotive SOCs. He has over 18 years of experience working in the semiconductor industry, and prior to joining the functional safety team, he held various leadership roles in the design verification domain. After that, we'll focus on the process formalization. We analyzed the way an FMEDA is done, we formalized the process, and then started deriving the data model to cover it. And Jake will give you great details about this. Jake is the functional safety solution manager for Mentors, a Siemens business, and is responsible for the strategy and the alignment of functional safety and high reliability technologies across the portfolio of IC verification solutions. He holds a Bachelor of Science degree in Electrical and Computer Engineering from the University of Colorado Boulder, and prior to Mentor, Jake has held various design, verification, and leadership roles performing IC and SoC development at Xilinx, Micron, and Broadcom. And then the last section is the future work. As we develop the data model, there are adjacent areas that are connected to it, and that's what we're focusing on, and Regis is going to give you a coverage of that. And Regis works for AMD as a functional safety manager. He has over 18 years of experience in functional safety for electrical and electronic systems and semiconductors by leading functional safety department in a tier 1 company and working in various semiconductor companies. He's part of the ISO Working Group 8 through the French delegation, and he has provided various content on ISO 26262 Part 11 and holds several patents in the functional safety area. So let me give you a very brief history and the statistics of the group. So we'll start at the bottom left on the green. In October 2019, we started with the proposed working group formation. You might know that that is the first step in an Accellera working group. In this phase, as you can see at the top, the group gathers the industry needs and the support that we would get in case the group is formed. And during this phase, what we have analyzed are the what and why. What are the pain points? Is there work to be done? Why do we need it? We had our kickoff 2 years ago, face-to-face in Munich. And after that, we spent a few months writing down, formalizing what we had gathered in the meetings and in a few online meetings and discussions, proposed to the board, and the group got the approval for the working group formation in February 2020. As you can see, in green, we had 30 plus companies during the proposed working group. We still have 30 plus companies. They are a slightly different set, but still a really strong support from the industry. After that, we held different virtual face-to-face. We were never actually able to meet. But on the blue is the standardization work, the execution, so the how. So we started focusing on really developing the data model. We published a white paper in Q2. It's posted on the website. Please, if you're interested, go and review it. We are working on the data model definition. We plan to publish a white paper in Q1, and hopefully the draft language will be in Q2. The stakeholders that you can see at the top right are IP, silicon system providers, and EDA. The group has a really strong support. There is a lot of work that we're doing, and you'll see all the details in the next few slides. And just a quick reminder before we jump into the meat of the workshop, please keep in mind that everything you see in this presentation is work in progress. It's the standardization working group. So as you can imagine, there are tons of discussions ongoing, and until something is published, things can change. Keep that in mind, and please enjoy the rest of the presentation. Varian, please go ahead. Thank you.
Thank you, Alexandra. In the next set of slides, we'll go through some of the challenges that we are facing in functional safety world and how we are planning to solve them in this functional safety working group. With the increasing demand of compute power, the electronic systems deployed in safety critical applications become more and more complex. As a result, the safety requirements also become more complex, and it affects all parts of the system, including hardware and software. Addressing these safety requirements result in various safety activities and operations. These are documented in ISO standard and they are referred to as work products. However, the standard does not strictly specify how this safety data is stored, exchanged, and integrated among different entities. Additionally, the format and language of this work product is also not standardized. This poses many challenges to the creation, manipulation, and exchange of data. The Accellera working group has identified 5 major categories of these challenges. This has exchange of the same safety information across different automation tools, connection of safety data with design information, sharing of safety data across different operations and work products in same layer, and also across multiple layers between suppliers and integrators. And the last one is traceability of information across the distributed working environment. These challenges are described in more detail in the next slide. In the last few years, there has been a lot of activity in development of the automation tools for functional safety. However, these automation tools are developed in parallel, and they don't support a common language or a format. For example, an FMEDA created by a supplier using one tool cannot be directly used by the integrator using another tool. Another example is when a preliminary FMEDA needs to be leveraged into final FMEDA. The second challenge is connection between the functional safety data and design information. When doing safety analysis, some information that is needed comes from the design metrics. For example, when performing final FMEDA and calculating failure rates for a failure mode, design information such as the area of the design, transistor count, or design hierarchy is needed. This is currently a manual process or custom solution is developed. Third challenge is sharing functional safety data across different work products in same layer. There might be several different safety related activities or operations performed within same layer. And these different operations, they require data that is dependent on each other. For example, when FMEDA is performed, the safety mechanisms and the failure mode information is contained in FMEDA report. This information now needs to flow to the design, implementation, and verification plan. Also, the verification metrics need to be back annotated to the FMEDA report. The fourth challenge is the exchange of functional safety data between different suppliers and integrators. For example, one integrator might be getting FMEDA report from two different suppliers. These two FMEDA reports might be in completely different formats. So now the challenge is on the integrator side to merge this two FMEDA report and create a system level FMEDA report. Second example is when one particular supplier needs to provide FMEDA to two different integrators. In this case, the requirement might be different from two different integrators. As a result, the supplier will need to create two different FMEDA reports for the same design in order to satisfy the integrator's requirements. The last challenge is the traceability. This is very important aspect of managing the functional safety development. This applies to both interlayer and intralayer functional safety work products. Traceability is basically key to ensure that there are no systematic faults that get introduced in the design and create an unacceptable risk for humans and the environment. The challenges outlined earlier require improvement in three different characteristics of the development process. First one is interoperability, which means the ability to accurately provide and integrate data across supply chain. Second one is traceability, which is the ability to bidirectionally trace and verify the history and connection of the information. And the last one is automation, which is the use of EDA tools to automate tasks of manipulating, storing, and exchanging information. The immediate mission of the Accellera working group is to provide a unified definition of functional safety data, format, and language to propagate data across the distributed development environment. Eventually, this enables the interoperability, traceability, and automation of data. To support safety critical applications, information needs to be passed or exchanged along two different directions. Interlayer is the communication between, say, IP to a component or a component to a module. For example, safety requirements might flow from upper layer to the lower layer. On the other hand, multiple safety activities might need to be performed in the same layer. For example, safety requirements might flow from the safety documentation to the design and to the verification in the same layer. As the safety life cycle proceeds, work products such as safety requirements, FMEDA reports, DFA reports, and FDA reports might be generated. It is therefore valuable to establish standard definitions of the data elements contained within these work products. Several standards exist today for the functional safety development lifecycle. While the IEC 61508 is applicable to several industries, there are also industry-specific standards derived from 61508. For example, ISO 26262 is specific to automotive industry. These standards provide best practices and guidelines that need to be followed in order to achieve the adequate risk reduction. The Accellera working group does not intend to define new practices. However, focus is on developing the functional safety data format and language that supports these guidelines. This data format and language will be consistent with existing standards, and focus will be on their enablement by improving automation, interoperability, and traceability. IEEE has also formed P2851 working group, which is complementary to the work being performed by Accellera. As in other successful standard definitions, once completed and published, the Accellera standard will be considered for contribution to the IEEE standard. The scope of the working group transcends across several dimensions. These are shown in this slide. The green boxes define the scope of the working group and capture how the work will proceed in phases. The initial focus aligns with the content below the green dotted line, while the content above the dotted line will be the future work. While the immediate focus is around the automotive industry, the work of the working group is planned to proceed incrementally and expand into industrial and to aerospace and medical industries. Similarly, the work started on digital domain will later extend into mixed signal and analog and other domains. And lastly, the immediate focus right now is on the FMEDA work product, but the work will again incrementally extend into other work products. The functional safety standard will include the safety content information in addition to and separately from the design information. In context of enabling tool automation, the safety standard will add to the design information data to traverse and support the entire development lifecycle. The safety standard will enable the functional safety aware design and verification flow by defining the data model to capture and propagate the safety content across the different safety activities in the same layer and also between layers ranging from system to the IP. In summary, key objective of the standardization process is to harmonize the best practices and terminology across the industry by a common language and schema. Also enable efficient interchange of data representing the functional safety context across the safety lifecycle and also among different organizations. And lastly, to be comprehensive, flexible, and scalable to meet future needs. Now, I will hand over to my colleague Jake to describe the data model in more detail.
Thanks, Aaron, for an overview of the challenges, mission, scope, and objectives of the working group. As mentioned previously, my name is Jacob Wilkin, and I'm the Functional Safety Solutions Manager for Siemens EDA Design and Verification Division. And I'll be talking about the process formalization and the creation of the data model supporting the functional safety content that this working group is focused on. First, let's take a look at the scope of the functional safety data that the group is looking at. Safety-critical standards require a wide range of work products, and the data populated in those work products is a result of expert-driven analysis and/or tools delivering this data. This includes data from safety activities and verification, analysis, requirements definition, and more. Additionally, functional safety data is generated and exchanged across different layers within the development lifecycle, which we have used the term intralayer, and also across the supply chain from suppliers to integrators, which we call interlayer. The primary goal of the data model effort is to form bridges between the various functional safety work products and the tools generating the functional safety data for those work products. It is important to note that this standard effort isn't focused on standardizing on a particular type of functional safety analysis, such as standardizing on the creation of an FMEDA, as much of this is already covered in existing functional safety standards. Our goal is to create a data model of safety data supporting the multiple methodologies which exist and are in use in the industry today, and ultimately enable the realization of requirements articulated in those existing standards. A layered approach has been adopted for the development of the functional safety content, where the focus is to identify and agree on the content first, followed by the development of a conceptual data model. The conceptual data model then drives the language and format of the functional safety data. Similarly, scope is layered based on dimensions, namely work product and activities, industry segments governed by the relative safety standards, and domains like digital and analog hardware and others. To help scope the data model efforts into bite-sized chunks, the group plans to collate and agree on the functional safety content for FMEDA from an automotive functional safety standard for digital components first. The task related to FMEDA data model has been layered into 3 steps. The first step is to arrive at a consensus on a generic approach which serves the concurrent practices and is flexible enough to serve the currently foreseen methods in the future as the product development methodologies and technologies evolve. Formalization of the functional safety analysis process is the first step, which leads to the development of the conceptual data model. And then finally, the activity shall culminate into a data model language, which will enable interoperability or the ability and effectiveness of exchanging information. As an example, this is the exchange of functional safety content across different automation tools and the sharing of different functional safety content across different operations and work products within the same lifecycle. Second is traceability, which is the ability to trace and verify the history and connection of the information by means of recorded identification. And the third element which is enabled is automation, which is the usage of EDA tools to automate the tasks of manipulating, storing, and exchanging information. And although automation will enable improvement in all of the challenges described previously, the most visible need is the connection between the functional safety content and the design. Defining the basic concepts around FMEDA has been at the core of the activities in the last couple of months in the working group. The first focus area is FMEDA types, of which 2 have been defined. The first is assumption-based, which is an FMEDA derived from pure expert or engineering judgment, and the second is a calculation-based FMEDA derived from safety analysis verification using techniques like fault injection and formal analysis and others. Secondly is the mapping between hierarchies. This includes the mapping between the functional safety hierarchy and the design, as well as the mapping between safety mechanisms and the design, as 2 examples. Third is the representation and connection of functional safety information, and this includes the connection between different design abstraction levels of the safety analysis, both on the inter and intra-layer, as well as across different activities in the life cycle, such as FMEDA, FTA, DFA, and more. Also in focus is the functional safety model elements and the associated attributes for those elements, as well as the safety mechanism and diagnostic coverage representation and aggregation for safety mechanism configurability. For the sake of clarity in the context of the data model definition, there are 2 types of FMEDA which we have previously discussed. The first is assumption-based FMEDA, where design metrics are estimated by the user. This is also commonly referred to as an expert-driven judgment or expert-driven population of FMEDA data. The second is calculation-based FMEDA, where the design metrics are derived from the design hierarchy and the related data on area. The calculation-based FMEDA is performed after design mapping. But it's important to note that the final FMEDA can be a combination of both an assumption-based FMEDA and a calculation-based FMEDA. The rationale for why this distinction is being made is that when the functional safety hierarchy and the failure mode hierarchy are linked to the design hierarchy, as is the case with a calculation-based FMEDA, the safety metrics are not assigned by the user but are derived from the design hierarchy. It's important to note that the distinction between the 2 does not imply a greater level of accuracy. A design may be represented in different but equivalent ways, like block diagrams and trees as shown on the left. From the design hierarchy, the safety analysis hierarchy is formed. And for a calculation-based FMEDA, the analysis hierarchy is then mapped to the design hierarchy, connecting the chain between the design hierarchy and the safety analysis hierarchy. Looking at this from a flow perspective, on the left we have the structural view of the design, and this can either be a tree representation, a block diagram representation, and either structural or functional. Moving to step 2, the functional safety analysis is formed based on the intended functionality of the design from the safety requirements point of view. It selects the design depth for safety analysis and assigns the safety relevance. And then subsequently, on the far right, each leaf of the functional safety analysis hierarchy can fail, and therefore failure modes are assigned to those leaves, forming the failure mode hierarchy. With some of the basic concepts covered, let's take a peek at the functional safety data model and the categories defined. At this point in time, data model support for FMEDA for an automotive ISO 26262 IC must contain information defining the functional safety analysis hierarchy, failure mode hierarchy, technology and reliability information, safety goals and requirements, safety measures, also commonly known as safety mechanisms, and the necessary mapping between safety measures, the safety analysis hierarchy, the failure mode hierarchy, and more. Diving one level deeper, this is a quick look at the data model entry for a safety mechanism. Certainly too much to go through in this presentation, but as you can see, we have defined a set of attributes applicable to a safety mechanism entry, such as name, diagnostic coverage for permanent and transient failures, the configurability of the safety feature, and more. We also define the type designation for those attributes, whether the attributes are required, and a description to help facilitate understanding of the usage of each attribute. Another example is the relationship between the safety mechanism and the failure mode. Similar to the safety mechanism entry, we have attributes such as name, whether it's active, and more. We have also defined the diagnostic coverage for single point and latent faults on the permanent side, as well as transient faults. It's important to note that these values are the expected safety mechanism coverage in the context of the failure mode the safety mechanism has been deployed to protect against. So it's a slight variation from the safety mechanism entry shown previously. And the final point I'd like to touch on today is an example of the interlayer exchange of data. An FMEDA for an IP may roll up to one or more higher level failure mode effects. And these failure mode effects are then used in the functional safety analysis at the larger component level, where IPs are stitched together to build out broader functionality. The failure mode effects represent the failure as seen at the top level of device under analysis when a failure occurs. And for a safety element out of context, these failure mode effects are often based on assumptions of how the device under analysis is going to be used when incorporated into a larger component. And it's important that the integrator understands and maps these assumptions to the component level failure modes. So hopefully this has provided a glimpse into some of the data model work completed and currently ongoing within the Functional Safety Working Group. To talk about some of the future work, I'm passing the ball off to my colleague Regis.
As we know, the ever-growing implementation of electronic systems for safety-critical applications is posing a growing risk associated to the possible failure of such systems. The definition of functional safety standards such as the ISO 26262 for the automotive industry or the IEC 61508 for the industrial applications and other standards is made with the intent to give a guidance to the suppliers of the system on how to mitigate those risks during the product lifecycle. Those standards have some differences on how to approach the safety analysis, for example, in particular on the metrics to evaluate the risk because of the architecture choices. Accellera did start to address safety analysis, focusing on the ISO 26262 approach. And further, Accellera will address the specificities of other standards and will address other safety activities also. As previously said, Accellera have started the work focusing on the safety analysis. But of course, functional safety needs to address various topics. The goal is to have the data model covering most of the key data manipulated and communicated during the development. This data is part of safety analysis, but not only. It's also part of plenty of the other activities during the development, such as requirements, verification, validation, etc. In order to address the various safety standard approaches, as well as the various topics, Accellera Functional Safety Group have created subgroups of experts. These subgroups follow the same process described here, to develop what needs to be part of this Accellera standard at the end of the day. The first phase is requirement gathering. In this phase, we establish the needs and the scope of the topic or the activity using brainstorming sessions, presentations. The experts share their experiences. The development phase consists in defining the data model or identifying the data that interface between the topics or activities. The publishing phase consists into creation of a work product that will be shared internally in Accellera or for reference or externally to be part in some ways of the final Accellera standard. For example, the safety analysis is always made with a lot of assumptions. You can have as an assumption the failure rate, failure mode distributions, the architecture allocation, etc. The phase of the safety verification confirm or disconfirm the assumption and adjust the metrics elaborated by the safety analysis. The functional safety group will identify what is the key set of data used by the different existing safety verification and validation methods in order to consider this set of data in the data model for the Accellera standard. So as previously explained, there is different angles that needs to be covered in the Accellera standard. The diversity of the functional safety standards and the different activities and topics make the interoperability complex. One of the main goals is to be exhaustive in the scope and make sure that we satisfy every of the domain of application and activities. The complexity implies very detailed technical discussion, sharing use cases based on the experience of the experts participating in the group. We make sure to identify in a systematic way all the interaction between the activities during the development. This work lead into the improvement of the data model itself, the definition of interfaces, and additional needs, for example, methods, constraints, etc. For more details, a white paper has been published and the link is given here. The white paper gives an overview to understand the challenges and the goal of this group. If you are interested in participating, you are warmly welcome to join. Please contact Accellera members to know how to proceed.
Hey, welcome back. Thanks for a nice, wonderful session, Sandra and team. So we'll wait for audience to type in their questions in the chat window. Right, we'll have another 10 minutes. So while we wait for audience to ask the questions, I have a couple of questions captured from the previous discussions. So first question I have, I think it's been clearly articulated that functional safety working group is closely working with other industries like industrial and aerospace as well, right? So I think big question that it comes in mind that industrial has their own standard for safety and aerospace, they have their own standard for safety, right? So what is your thought in terms of collaborating and coming up with a common framework towards the safety?
I'll take the first 30 seconds, then anybody else that wants to add. It's going to be, what we saw is that it's been an interesting challenge to already kind of agree internally to the team, and most of the team was expert on the automotive side. So it's been interesting to come to a common ground already. So the plan is to extend, as you said, to the other domains. And we are in contact, at least with the industrial standard team. And we plan to extend it to the aerospace as well. But it's going to be interesting to see how much it can be extended, how much people will find commonalities there are. But we thought it was also quite easy to do it on the automotive side to talk the same language, and instead was quite challenging. I don't know, Regis, Varin, Jake, what do you think?
No, yeah, I agree, and I think also the really basic type of data will be kind of the same type, right? I'm not saying the same that like for example the failure rate and the failure modes. By the way, it's really the basics of the data. The way we are managing those can be a little bit different. And yeah, we plan really to make sure that our model will be, of course, we are not including the calculation, so it's going to be different from a domain to another. But of course, we want to make sure that it's going to be used in all the models. So there will be some adaptation that we need to do for that.
I think the one comment I'll make is to emphasize is the work that we're doing is to augment and complement the existing safety standards, whether that's a 254 for avionics or 61508 for industrial. The work that we're doing is to complement those existing standards, not to sort of necessarily influence or provide conflicting messages. It's purely a complementary work.
Okay, wonderful.
If I may pick up, yeah, sorry, Lokesh. No, if I may pick up on what Jake just said, I think this is actually a very important point. I think this was covered in the presentation, but it makes sense to reiterate. We're not planning to change the best practices that are already established. The plan for us is to come up with a data model formats that actually enables more automation to implement those best practices. That's what Jake was sharing, which I think it's a very key point for us to make clear that we're not planning on developing a different standard or an additional standard. Yeah, it's more for enabling the existing ones.
Yeah, that really makes sense also. I think there is no point in reinventing the wheel again. Should reuse the framework we've already defined and see how do you.
Lokesh, we can barely hear you.
Can you hear me now? Is that better?
Yes. Yeah.
Okay. Yeah, I think I just repeating your point, I think what you mentioned is right. And there is no point in reinventing again different framework for the aerospace and other domains.
Again, Lokesh, you're coming in and out.
Okay. Let
anyway.
me see. Yeah. So let's move on to the next question. I think one question from the audience. The question is about, I think we spoke about a lot about the digital verification. So what is the scope in the standard for analog and RF and mixed signal?
Does anybody want to take that?
Yeah, I can take this. Oh, Jake?
No, go ahead, Regis. Go ahead.
Just wanted to say also, the people also are kind of the majority are really a semiconductor and automotive and let's say digital, but we have also some analog people participating. So this is absolutely important for us to cover all the aspects. So I would say digital, analog, and even system level. And so it's we are really cautious because you see that there is different levels that we want to cover, of integration, and especially because we want the communication between the different layers to be smooth and good. It's really important to have all those viewpoint points, and so yes, it's covered.
Yeah, and I think the one thing I'll add is this presentation and what we're currently focused on is FMEDA enabling the creation of different approaches to FMEDA, and the work that we've been doing does not prohibit the creation of a FMEDA and a mixed signal device that supports mixed signal, digital, and all the different variants that you would expect from an IP or IC supplier.
Yeah, exactly. So like Jake was saying, right? So for example, if you take an example of fault campaign, right, you might be doing fault campaign on a digital domain or kind of analog domain, right? And both results, they need to go back to FMEDA. So yeah, it needs to kind of go to both domains.
If I can just pick up on what Regis said, he said it, on the way, but I think it's actually, a side comment, very important. As we talked in the team, as we gathered the requirement, I think the number one pain point has been the communication in between, the different layers, right? And so Regis just mentioned it as, one of the things. I would just like to say that I think it's really one of the key points that everybody brings up as the most painful part, communicating and exchanging information. So it's not just about the digital and the analog, it's really also in between different players in the chain. Yeah.
Okay, thank you guys. I think last question what we have for today is, I think it's more related to software. I think the question is, while the engineer is designing the hardware, what do they need to worry about software safety? Do they need to really look at software safety early while doing the hardware design? Or if yes, how do they can connect both of them? Any comments on that?
Yeah, I take it. Okay, as a first, and please comment after that. So of course there is software aspect, and if we consider, for example, the safety mechanism that we can consider in the case of the FMEDA, there is a couple of things that the software will handle, right? And so that will participate, and of course will have an impact on the calculations that you will have at the end. This is for the FMEA, but of course there is plenty of other activities on the functional safety in general that the software piece are having impact on the hardware and the system, let's say in a way, which is, for example, the requirements, and it's also a part of the future work that we are going to do. The requirements, the communication of the requirement, and specifically some attributes for the functional safety. We started that work also. So it's part of the future work that I was covering in the video, and basically this is the idea is to make sure that we identify the type of information, the attributes that will be communicated from an activity to another, and from a layer to another layer, and from a company to another company. If there is a partnership or customer supplier relationship or things like that. So yes, the software is having impact, and in terms of analysis, it will be more further work that we will do. At the moment, we are looking at the interfaces.
Yeah, I think to add to what Regis was saying, right? So one example is the software test libraries, right? Those might be running on a processor, and you might be claiming some kind of a diagnostic coverage for those software test libraries, right? And this information you specify in FMEDA report, now it needs to go to verification. They might be running for campaign on those STLs. And the proof of the diagnostic coverage, you will need to back annotate to FMEDA, right? So that kind of information is kind of what will be required from software to design to verification and kind of back to the FMEDA.
Yeah, so thanks for sharing your thoughts around this point, guys. I think with that, we'll end the session for today. So again, thank you very much for joining and sharing your thoughts and ideas. So Alessandra, anything that you want to add before we close the session?
No, thanks for hosting us. Thanks a lot for the 3 speakers to join. Sometimes, like, some of them are ungodly hours. None of us is based in India, so thank you very much for that. And if anybody is interested in the group, I think you have the references in the slides. Please reach out. We are open to new members that wants to contribute. Yep.
Okay. Thank you very much. See you again.
Thank you very much.
Thank you.
Thank
Bye.
you. Bye. Bye. Bye.